In this lesson, we're talking about the fundamental counting principle. In the last lesson, we talked about a couple of different ways to figure out how many different outcomes for a particular set of events are there. We looked at making a table, making a tree diagram, but here we want to look at another option that gives us a way to easily count things that have a lot more outcomes. Okay, so for example, Joey has 5 shirts, 3 pairs of shorts, and 2 pairs of shoes. How many different outfits can he wear? Assuming that an outfit has 1 shirt, 1 pair of shorts, and 1 pair of shoes, we could make a tree diagram. Okay, we could do 5 shirts, and then we could branch off 3 pairs of shorts from each of these, and then from each of those we'd have 2 pairs of shoes. And we can see pretty quickly that's going to get really crowded, and it's going to be really hard to do, especially if he had 50 shirts and 30 pairs of shorts. So we want another way to do that. And what we're really considering with the tree diagram, to answer the question, how many ways can something happen, is we want to know how many different outcomes are there at the very end of the branches, and is there another way to get that number without listing everything, okay? And it turns out that there is, because each shirt goes with each pair of shorts, okay? Then we have 5 shirts times 3 pairs of shorts to match with each of those, and then 2 pairs of shoes to match with each of those, so then we would do the 5 shirts times the 3 pairs of shorts times 2 pairs of shoes, and we get something like this. So we've got 5 shirt options, we've got 3 shorts options, and we've got 2 shoes options, and we see that there are 10 times 3, 30 different outfits that he can wear. And again, that's going to be a lot more convenient than trying to make a tree diagram of all of those outcomes, okay? What we've just used here is called the fundamental counting principle, which states if an outcome consists of k independent events. Remember, independent means the outcome of the first doesn't affect the outcome of the second. So like when you're talking about rolling dice, rolling a 3 the first time doesn't change your possible options for the second roll. Okay, the first can happen in n1 ways, the second can happen in n2 ways, the third would happen in n3 ways, n4, n5, all the way to nk for the kth option, for the kth event, however many k is. Then the number of possible outcomes for all of those events together is going to be the product of the options of each one individually. So n1 times n2 times ... up to nk, okay? So to do this, we still want to be systematic about it, but to do this, what I strongly, strongly recommend is that you draw blanks to represent each of the events, label those blanks, okay, like I did up here, okay? And then ask yourself, how many options do I have for the first? How many options do I have for the second? How many do I have for the third? Ask individually, okay? And that's the important question there. And then we'll multiply all of those together, okay? So for example, the first question says, how many ways can first place, second place, and third place be awarded to a group of 50 contestants, okay? And so I have 3 different events happening. I've got first place, second place, and third place, okay? And I ask myself, how many options do I have for first place, okay? It's not 3, all right? It's not the number of blanks that I drew, but it's how many different contestants could get first place. Assuming that, there's no restrictions and this one got disqualified or something, there's 50 different outcomes or 50 different options for the first event, okay? Which is first place. And then second place. Well, really, I have 50 to choose from for second place, but one of those has already gotten first place. And it's really unlikely that somebody who gets first place can also get second place for a particular event. So really, we only have 49 options for second place. Now, doesn't this say that we have 50 different first places? No, it does not. It says how many options did we have. We only chose 1, okay, but we had 50 to choose from, and then 49 to choose for second place. For third place, then, we actually have 2 different contestants that have already been assigned a place. So there are 48 contestants remaining here, okay? Can't be the same person that got first or the same person that got second. So there's 48 people left, 48 contestants left to possibly get third. So we have 50 times 48, times 49 times 48. We multiply those together, we get 117,600. Okay, so 117,600 different ways that 50 contestants get first, second, or third place, which means it's a really good thing that we didn't try and do that with a tree diagram. Okay, all right, next one. A coin is flipped, a spinner with spaces numbered 1 through 10 is spun, and a vowel is chosen. How many outcomes are possible? So I see that I have three different possible events. Okay, so I'm going to draw 3 blanks and label those. I've got a coin, I've got a spinner being spun, and I've got a vowel being chosen. And then that important question, how many options for each? For a coin, I could have an outcome of a head or a tail, so there are 2 options. For the spinner, it tells me my spinner is numbered 1 through 10, so I have 10 options for the spinner. And then a vowel, it doesn't say English language, but I'm assuming English here. How many different vowels can we choose from? There are 5 vowels, A, E, I, O, U. So of all of those, we multiply these together and we get 10 times 10 is 100 different outcomes. So 100 different ways that we could flip a coin, spin a spinner, and choose a vowel. Okay? Another one here. How many ways can 5 books be arranged on a shelf? First question we want to look at is how many different events are there? Okay? How many events are there? Well, there are 5 events because here the events represent the positions on the shelf. So we could do this a couple of ways. We could say what's the first position, second, third, etc. Or we can say we're numbering them or we're placing them from left to right if we want to do that. But we need something to indicate, yeah, there's 5 different spots for those books to go on a shelf. Okay? And then we ask ourselves, for the first one, for the far left book, how many different books can go in that spot? Well, there's 5 books to choose from. And then for the second spot, one of the books has already been placed. Not all 5. There were 5 to choose from, but one of the books is already there. So no matter which of the 5 was chosen, there are 4 books remaining to go in the second spot. Okay? And then for the third spot, we can say there's one that's already on the left, one that's already in the second to left spot, so there are now 3 books left to place in the middle spot, okay? And then you can probably guess what comes next. We've already placed 1, 2, 3 books, so we have 2 books remaining. And then how many books can go in the last spot? Well, there's only 1 left, okay? So only 1 option. We multiply 5 times 4 times 3 times 2 times 1 gives us 120 different ways, okay? And if you're interested, there is a little bit in your book where you can look up something about factorials. Factorials are where we put an exclamation mark behind a number. Okay, so it looks like it says 5, but really it says 5 factorial is how we would read that. We're not going to do anything with factorials in this section, okay? But there is some interesting stuff that happens, and they are super useful when you start getting into really huge numbers. Like if we had 500 books and we wanted to arrange 70 of them or something like that, I really don't want to multiply 500 times 499 times 498. I don't want to do that by hand. So factorials give us a nice, easy way to do that. Okay? Again, not necessary, but is interesting stuff if you want to check it out. Okay, for the last example, oops, too far. How many ways can a committee man and a committee woman be chosen from a group of 9 men and 11 women? Well, I have 2 events happening. I've got the committee man and the committee woman. So I'm going to draw 2 blanks. Committee man, committee woman. Okay? It does not matter what order I label these blanks. Okay? It doesn't matter if I say, hey, Annie, you're the committee woman, and hey, Chris, you're the committee man. I could say, I could name Chris as the committee man and then Annie as the committee woman. It doesn't matter what order I say it in, I still have the two independent events, okay? And then we ask, how many options for committee man? Well, there are 9 men, so we have 9 to choose from here, and there are 11 women, so 11 to choose from for committee woman. I'm multiplying those 2, and I get 99 possible outcomes, all right? So again, with the fundamental counting principle, the important thing is asking yourself first, how many events? Draw those blanks, label them, and then ask yourself, how many options for the first event, how many options for the second, how many options for the third, etc., and then multiply them all together.